Okay, the record is now on. So let us go back to where we have here. Now, we have the most important thing, that is the global stiffness metrics, but still this is for just one member. So the next step is we need to, find a way to put them together so that the metrics would represent the entire structure. Okay, so here we are as an example. Let's just take a look at the system. Okay, and now this is the system that I've been using in the past like decade or so. Pardon the say the boring structure, but I think it works, and I don't think anyone in this class got a bad grade before they just drop out. Okay, so let's say now we have the structure now, and let me tell you before we move on that this is not a joint. Okay, it's just two member, one like that and one like that. Okay, so now we have the system that consists of say 1, 2, 3, 4, 5 members. So the easiest thing is just to give it the names first. Okay, and like let's hope that I don't make a mess here. So let's say this is going to be member number 1. And I'm going to go and say, this is my member number 2. This is my member number 3. This is my member number 4. And this is my member number 5. Okay. Now we have 5 members. Notice that maybe it's useful for some, but I don't think we need this. But you see, this has 4 joints. 1, 2, 3, 4. Okay. Joint numbers is, okay, so that you know that I have given this. Now when you look at member number 1, it's in this direction, but to be able to give it a proper rotation as the trigonometry function, you need to know where it begins and where it ends, right? Because you can only give the proper sine and cosine values to the member only when you know the orientation of the member. So how do we find the orientation? We find the orientation by giving it the local 1, 2 node, right? So I can say if this is going to be my member number 1, I'm going to say this is my local node 1, that this is my local node 2. It's like a vector. If I use this as a 1 and 2, it means that the vector for my member number 1 is this one. Okay. Another way around, if I call this 1 and 2, 1 is always the first node. So your vector points towards 2, and this is going to be my orientation. So you see, this and this will give you different trigonometry numbers. Correct? This has the positive sign. This has a negative sign value. Cosine is 0, right? So the orientation is important in that regard. Okay. And remember, we need the sine and cosine terms in our transformation matrix. So I'm going to use this as 1, 2. So that becomes the orientation of my member number 1. And for my member number 2, let's play around a little bit. So let's call this 1, 2. Okay. You know what? We don't need the node numbers and it gets in the way. So after I show you, I'm just going to erase it. So the orientation of member number 2 is like this now. You see? So in terms of transformation metrics, it's going to be different from that of member number 1 because of the orientation of the member. Now for member number 3, I'm just going to call this 1 and 2. Okay. Member 4, 1 and 2. Member 5, 1 and 2 like this. So now we have all the members with the local coordinates in place. Let's take a look at the entire structure. And again, because this is the displacement method, first and foremost, you need to be able to identify the unknowns of the structure, right? Remember, this is the truss. How many unknowns? Can anyone try? Remember, this is the displacement method. And this is the truss. So it's a two-dimensional system, the two force member. It's a displacement method. So how many displacements do you need to solve for this truss? Remember that this is not a joint. How many displacements you guys need to solve? All quiet. See, it's pretty simple for kids to forget the most important thing in structural analysis, the identification of the unknowns. In this class, we have not done any force method at all. We have done only the displacement method, and yet you cannot answer. Brilliant. Okay. Anyway, excuse me. So we can have displacement here. You can have displacement here, 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 and here. Okay. I don't know why I use Q, but it say it works somewhat. So you have displacement number 1, Q1, Q2, Q3, Q4, and then Q5. So this system is 5 degrees of freedom. Correct? You can have 5 unknowns. In other words, it means if you know these 5 unknowns, you can describe the structure any way you want it. Okay. So interesting enough, the Q is used for displacement. So what are we going to use for the force? Maybe another Q. How many forces we can have? Let's say if we apply the force at the support, what's going to happen to the structure?
So wait.
You apply the force to the support of the structure, what's going to happen? Listen to the question very carefully. If you apply the force to the support of the structure, what's going to happen?
Reaction.
Yeah, you could say that. And what else? Think about it. If you apply the
Deformation.
huh?
Deformation.
Really? If you apply the force to the support of the structure, what is going to happen? Like this. If I apply the force here, what's going to happen? Besides the reaction. Actually, it's a very basic question, you know. This question should be in statics, not should be in here. In the meantime, let me fix the Q. You don't know? Nobody knows?
What about moment?
Moment? This is the trust system. Why are we talking about moment?
Oh, I see. I see.
If I apply the force to the support, what's going to happen? Okay. Support. Anyone? You want beam? If I apply the force here, what's going to happen? What? Oh, wow, it's all quiet. If I apply the force here, what's going to happen?
Support gonna receive the force.
What? Yes, that's the same answer. It's a reaction. Yes, support's gonna have reaction. It's gonna receive the force, and what's gonna happen? Oh, gracious me. Answer is nothing. Correct? Nothing's gonna happen to the structure because the support takes everything. Doesn't look like 5 anymore. Fix this. So that means the only meaningful forces to the system is the forces applied in these degree of freedom direction. We call it Q1, Q2, Q3, Q4, and Q5. Correct? Now, enough of that. This is basic statics. I shouldn't have really spent this much time talking about it, but anyway. So now let's talk about member 1. Do I have it here? Oh, I don't. That's fine. Now, let's take a look at member number 1. Let's use the dark blue. Now, this is my member number 1. I have the, excuse me. Oh, I have the local node 1, 2. Okay. Meaning, if I go back here and I try to apply this global system, see, D1 and D2 must be at node 1, and D3 and D4 at node 2. So when I look at my member number 1 now, it means that I should have, what color should I use? It doesn't matter. Try to give you guys some colors. How about this? So this should be my delta 1, right? My D2. Remember, this is the global displacement of member 1. And this is node 2, therefore this is D3 and this is D4. And D1 and D3, the odd numbers, are in X direction, and D2 and D4 are in Y direction. Okay? So this is member number 1. Now, from this information, now we know that our system here, you have displacement at this joint, and then this. And now you know, because we say, so we don't know how much it is, but we know we're going to call this Q1, the displacement of the system. Okay, so here we're going to call Q1, and here we're going to call it Q2, which means that you come back here. Now you know that this is Q1 and this has to be Q2. Are you with me?
Yes.
What about the rest? Ladies? No? Are you with me?
Yes,ค่ะ.
Oh, thank you. It's very refreshing to hear lady's voice. Okay. Now I can simply write the displacement of this member. This is D1. D2, space is not nice. Let's do it again. D2, D3, and then D4. Now we know. You know what D1 belongs? D1 is right here. It's the displacement of the local node 1 in X direction of member 1. And incidentally, this is where your support is. So this has to be 0. Correct? And D2, it's the global displacement in Y direction at node 1 of member 1, which is here. So again, it's a hinge, so it has to be 0. Now D3 is the global displacement of node 2 of member 1, but now it's at the joint where there is no support and it is going to displace. We don't know how much, but we have given the designation that we're going to call it Q1. Okay, so here is Q1. And similarly, this is going to be Q2. So are you with me so far? Are you with me?
Yes, yes.
Would you like to try to do this for member 2 yourself? That's member 2. Let me give this to you. For member 2, remember, for understanding and for fun, I have deliberately called this local node 1 and local node 2, meaning this time, because at local node 1, we say this is going to be our D1. This is going to be our D2. This becomes D3 because it's node 2, and then become node D4. Okay, and now you would know that for member number 2, now there'll be a lot of displacement for this member, you see, because this joint will displace both in X and Y direction, and this joint will also displace. Now to differentiate what member you're working on, again, I dropped the superscript to reduce confusion, but in fact, when you write, you should always have the superscript to give the information that you are working on member number 1. Like that. Okay, so I'm going to give you like a few minutes to try to do it yourself for member number 2. Okay, then I'm going to tell you, please try to do it for your own benefit. Okay. Okay, let's see if you can do it. And do ask questions right away if you have any. Okay. No, no, while waiting, at least I can write this, right? D1, D2, D3, and D4. This time it's going to be for member 2, right? Can you do it?
Yeah, yes.
Oops. Oh. Okay, you guys finished now, I hope.
Yeah, yes.
Okay.
Yes.
Yes. What about you ladies? Hello?
Yes,ค่ะ.
Thank you. So, it doesn't hurt to try to give the designation here and what's going on. So the capital D1, the global displacement for this member 2 here should be equal to Q3, right? This D2 should be equal to Q4. And here we have another one, Q5. So this is D1 here is Q3. This is Q4. And this is Q5. And this one, the last one is 0. It doesn't move because it's a support. Okay. So it's in similar fashion, I think we can carry on and do it for all the members. Okay. So let's say for member number 3. The local system, this is the node 1, 2. So that means this becomes the D1, D2, D3, and then D4. So basically, our member number 3 is just in the air, right? It doesn't connect to any support at all. So we must have all the displacements. Well, here, okay. This is Q1. This is Q2. This Q3, and here is Q4. So I can just write the matrix here now that as too short maybe. D1, D2, D3, and D4. That's going to be essentially Q1, Q2, Q3, and Q4. Okay, and yeah, that's it. Now, I think when you begin to get a hang of this, you don't need to write everything, 3, 3, and 3. I can just go ahead and write this matrix for member number 4 and 5 right away. If you don't want me to draw the picture of the member, do you think we can live with that? Can you draw the pictures of the members yourself, or you want me to draw it? If there's no response, I'm just going to draw only the matrix. I'm just going to write only the matrix,
It's your call, teacher.
Pardon me?
Yeah, it's your call.
It's my call. Okay, if it's my call, I'm just going to write the least writing part. Okay, so for member 4, you can just look at the picture and try to get it. Okay, D1, D2, D3, and D4. In fact, you can go back and look at member 4 here. This local node 1 is only Q5, right? And local node 2 it's 1, 2. So it's not that difficult really. This is 0, right? Because here for member 4, D2 is in Y direction. This is local node 1 of member 4, and Y direction is 0 because you have a roller here. So you have Q5 for D1. And then Q1 and Q2, right? It's pretty simple. And for member number 5, geez. Let me try to break the line here so that you don't get confused. Okay, so 5, D1, D2, D3, and then D4. So let us take a look at the 5 together. 5 is this one. Okay, you see node local node 1 is where the hinge is, so this better be 0, 0. And node number 2 is at the free end. So the displacement here must be equal to Q3 and Q4 respectively. So this is going to be 0, node 1, and then Q3, right, and Q4. Okay, and after you're done with this, it's a good idea to come back and put the superscript on it so that you know it's member 4. And this is 5. Okay, any question? Simple enough, right? Now, the next step is that I can I can put this together, this matrix, you know, let's say this one, this, and this to form another matrix. Okay. Now I think I'm going to stop writing the Q. Okay. So Q1 and Q2, I'm just going to write 1 and 2. Okay. So for this, it becomes 0, 0, 1, 2. Okay. That's for member number 1. Okay. And for member number 2 here, we have 3, 4, 5, 0. That's for member number 2. Okay. Member number 3, you can see it's 1, 2, 3, 4 here. So it's 1 and 2 and 3 and 4 for member number 3. For member number 4, just right on top of you now, here it's 5, 0, 1, 2. And last one, it's 0, 0, 3, and 4. So you see, let me change this color into pink. Oh, I just got that too. See, lasso just touched me. It's disgusting. Anyway, do this, right? Change it back. Okay. Now, you see, that is the members, right? We have 5 members to form this system. So it's 5 columns you have. Each column represents each member. So anyone tell me what is this? We have here 1, 2, 3, 4. What are they? This is the degree of freedom of members, right? When you look at one member, one trust member, it doesn't matter what direction you're in. When you look at the global direction, you always have 4 degrees of freedom for one member, correct? Because it's a trust and each member has 2 nodes, no more than that, right? So 2 degrees of freedom per each node. So in total, one member should have 4 degrees of freedom. So this is the number of rows will always be 4 for the trust, because the number of rows would represent the member's degree of freedom. And this entire thing is the degree of freedom of the system. Because, you know, each member has 2 nodes. Each node has 2 degrees of freedom. So each member has 4 degrees of freedom. But when you look at the entire system, this system has 5 degrees of freedom. Okay? It could have more, it could have less. Degree of freedom of the system is not the same. It doesn't have to be the same as the degree of freedom of the member. And, you know, sadly, some students never understand this. So I can give you a complicated structure like this, for example. Say, whatever that is. Okay. Now, if you have structure like this, the row of this matrix will always be 4, because each member can only have 4 degrees of freedom. But now how many members you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you're going to have a 4 by 13 matrix, correct? It's always 4 rows, because each row is 4 members, and then you're going to have 13 columns representing 13 members. And the numbers in the matrix could be, you know, how many degrees of freedom we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So you could have number 1 to 13 in here, representing 13 degrees of freedom of your structure. Well, incidentally, it has to be the same number, 13. So let me change that so that you see the difference. Yeah, no, it has to be the same. So it doesn't matter. Yeah. The number of degree of freedom, it has to be the same. So yeah, right, that's correct. So it doesn't matter what you change. So like that. Okay. This matrix is called Can I erase the picture of the trust below, or you want it? You want me to keep it? Okay, no response.
Just keep it.
Okay, thank you. This is the delay. Okay, this is what we call the local destination matrix, or L. Sometimes it's called member or member code matrix, M. It's a matrix that tells the relationship of the displacement of the entire system with the displacement of each member. And incidentally, we can use this to assemble the stiffness matrix of the system. Okay. And now for this, because now listen carefully, this is the system with 5 degrees of freedom. You see, the most important thing here, it's a 5 degrees of freedom. So you have 5 unknowns. You have 5 possible locations that you can put the force in. and you will have 5 displacements as the answer. So the huge picture in terms of the equation, you will have F equal to KD. The force matrix will contain F1, or I should write the, I wrote down Q here, right? Yeah, let's say Q is a real force, so I'm gonna mess you up a little bit. F1, F2, F3, F4, and F5. Because I write F instead of Q because we may not have, you know, force at every location. Okay, it's going to be equal to K D. And displacement here, you're going to have displacement D1, D2, D3, D4, and D5. The values like the Q's. Okay. Now let's take a look at the size. You have 5 degrees of freedom. So it means that your force matrix size has to be 5 by 1. 5 here, it's just exactly the number of degree of freedom. And here is your answer that you're looking for. It's a 5 by 1 matrix because you have 5 degrees of freedom. So to solve this means that your stiffness matrix has to be a 5 by 5 matrix. So the bottom line is that the size of the stiffness matrix of the system has to be related to the number of degrees of freedom. If your system has 5 degrees of freedom, your matrix, the force must be 5 by 1, displacement 5 by 1, and the stiffness matrix is therefore 5 by 5. Up to now, do you have questions? Any question? Are we crystal clear? Are we?
Yeah, yes.
What about others? Hello, senior.
Yes,ค่ะ.
Thank you. Thanks a lot. What about Mr. Ryder?
Yes, go.
Okay. Who else we have here? Nutipong doesn't have microphone. Napat, you still around? Atakon. From 50 something, now we're down to this much. This many. Oh, you're good. All right. You know, I think most of you who are here, I think you understand everything, but you make mistakes in the exam. Why? Because you don't practice enough. So, you know, it just only put a little more effort and you do very well. Okay, so now we are going to go back here. Remember, we have the formula for, oops, sorry. It's not in here. We have the formula supplement. Sorry, it's here. There. This is the formula for the global stiffness matrix of one member. Remember? So I'm not going to calculate this yet. I just want you to see the concept. Okay. So for member number 1, instead of writing those formulas, I'm just going to write the matrix, but make it big and call the component like this: K11, K12, K13, K14. So in the second row, K21, K22, K23, K24, K31, K32, K33, K34, and K41, K42, K43, and K44. Okay, so it doesn't matter what they are. Okay, you just know that this is the global. The keyword is global stiffness matrix of member one, just one member. Okay, member number one, not the system. But now what we have from the previous action is this matrix. It's a code. And for member number one here, the code is 0, 0, 1, and 2. What does the code say? The code says that we are going to take the components from this global stiffness matrix of member number one and put it in the global stiffness matrix of the system. How are we going to put it? We're going to put it by using the code, and now we have the code 0, 0, 1, and 2. 0, 0, 1, and 2. So what essentially the code tells us is that this K33, you see, it's 1 and it's 1. So the code says that whatever this number is, this component in this matrix will go on into the row 1 and column 1 of the global stiffness matrix of the structure. Let me try and write down for you. Code. Say K33 will go into the first row. Say, can I write like that? First column of the global stiffness matrix of the structure. Now we are pulling each component from the member into the structure. And in similar fashion, K34 of member 1 will go into the first row, second column of the matrix of the structure. K43 will go into the second row, first column of the global stiffness matrix of the structure, and K44 second row, second column. Any question? So I can simply write this. I can change this into the form for the stiffness matrix of the structure. Now we know it's going to be a 5 by 5. And the contribution from member number 1, after looking at the code, will look like this. K33, K34, K43, and K44. So this is the first row and the second row of the global stiffness matrix of the structure. And from the first member, the third column, fourth column, and fifth column of the first and second row, it has no contribution according to the code, so it becomes 0. And then the rest. Okay, so this is just from the first member, for member 1. Any question? Actually, you know, let's say if I never mentioned that this is the structural analysis, I give you a game to play and okay, can you do the coding like this? You know, I give you the code and can you put it in this fashion? Even kids can do it if they don't think this is structural analysis, right? But when you realize that this is the structural analysis, you say, oh, this is going to be difficult. Oh no, I can't do it. So let's say, you know, one day in high school, I go to your school and then I give this game for you to play. Can you do this? I believe you can do it with ease. It's very simple, right? And we can do it in the similar fashion for the rest of the members. So I think we are approaching the break now. So let me demonstrate with just one member and we're going to try to do the rest in the next hour. Okay. So any question? Hello. Hello.
คิดต่อเคลียร์ครับ
Okay, so I think
No question.
good, crystal clear, right?
Yeah, yes.
Good. So let's have a 15-minute break this time. So we should come back about 11:45. All right.
Okay, okay.